Let's talk about significance. The word significance has two different meanings when we're conducting data analysis. The first meaning is similar to the way you would use the word significant in conversation, meaning something important, something significant. The second meaning is more specialized when we use the word statistical significance. Something can be statistically significant without being important. Okay, now if you're confused by that, don't worry about it. If you have not had statistics yet, don't worry about that either. We're not going to do any math. Well, we might do a little bit of subtraction, but no real mathematics. Anybody can learn this. It's not difficult. Let's start with the concept of statistical significance. I have defined this in your notes as the probability of obtaining results at least as strong as those observed in your table, even if your hypothesis is wrong. This is naive language. A professional statistician would not use these terms, but it's good enough to get us started. You don't need to know anything else until maybe you get to grad school and start taking graduate level statistics. In other words, we know that there can be random errors built into our analysis, into our data collection. Error can creep in anywhere. And sometimes you might get a result that looks meaningful, but really isn't. It's due to randomness. So we have some mathematical tests that can be used to test whether our results are due to randomness or not. Again, this is the naive way of saying it, but it's a good starting point. So we have a mathematical way of doing this. You don't have to do any math. The computer will do it for you. Let's look at the table. So I have selected a question about your support for capital punishment as my dependent variable. We use sex as our independent variable. And I'm going to, in output options, I'm going to click summary statistics. Note what I did there? Clicked on output options, then summary statistics. I'm going to run the table. And there's our table. Now you can see that the table just looks like all the other tables you've made, but we've got something new underneath the table. We've got some output that you have not seen before. By clicking that checkbox for summary statistics, I produce some new stuff over here. And these are all tests of statistical significance. And the one we're going to focus on is P. P stands for probability. And the naive way of interpreting this is the probability that your results are due to randomness. So you can see here in this table, the probability is 0. In other words, the software is telling me that it thinks there's almost 100% chance that my results are statistically significant and not due to random error. Let's try another one. I'm going to use a GSS survey question called ABANY. I've typed it over here in the selected box. I click on View, and you can see what they asked. If you're playing along at home on your own computer, you can do this yourself. If you can't read it on my screen on the video, do it on your own computer. Please tell me whether or not you think it should be possible for a pregnant woman to obtain a legal abortion if the woman wants it for any reason. And the two meaningful responses are yes or no. So let's make a table with that. I'm going to leave sex as my independent variable. Run the table. Now we're going to test for statistical significance. Again, we look at the p-value, it's 0.02. 0.02 means 2%. The software is telling me that there is a 2% chance that this result, this difference between men and women, could be due to random error, just to random noise in the process. You can see that the difference between men and women is very small. It's less than 1%. If I subtract 39.6 from 41.1, it's a very, well, it's less than 2%, I should say. Very small difference between men and women. And p-value is saying, well, that may be a small difference, but it's statistically significant. It's not due to random error. Note here that my sample size is 33,460. That's how many people have answered this question. That's a lot. Now the p-value is impressed by large numbers. When you have a survey with a lot of people answering a question, P is almost always going to tell you that your results are statistically significant. Let me show you what happens when we, let's just do 1 year. I'm just going to do, we're making a selection filter here. Year equal, year in parentheses 2000. Let's see if that works. Yes, it did. So what I did there, let's go back. Selection filter, I'm just telling the software, only give me the results for the year 2000. The first table that we just looked at had all the results from every year they asked this question. I'm saying now I don't want every year, just give me the survey from the year 2000. And that's what we have here. And now you can see the difference between men and women is even smaller. Now it definitely is less than 1%. And P is much higher. Remember, P was 0.02 before, now P is 0.77. So 0.77 means 77%. The probability is 77% that this difference between men and women is just due to random chance. Or to say it another way, there is probably no meaningful difference between men and women. It's highly unlikely this table is statistically significant. So I'm going to make a rule. If P is less than 0.05, the table is statistically significant. This is our rule. So we're saying if there's a less than 5% chance that our table could be due to randomness, we're going to accept it as significant. That difference is between men and women is meaningful. No matter how small it is, we're going to accept it as meaningful. Now, again, remember that I made the table twice. The first time the software said that P was 0.02. The second time, P was 0.77. The only difference is the number of people surveyed. The first time, I had 33,000 and change people, more than 33,000 people answering the survey. When I look just at the year 2000, I have less than 2,000 people. So the software has given us two contradictory results. One is saying it is significant. The second table is saying it's not significant. Which one do I believe? Well, again, the p-value is impressed by big numbers. So I'm more inclined to believe this table we're looking at right now because the sample size is not too big. It's more within the realm of reason. So my general rule is that if the sample size is bigger than, say, 2,500 or so, I'm probably not going to trust P. That's just my personal rule. Another analyst might have a different rule of thumb. My personal rule, and the rule that you should use in this class, is that if sample size is greater than 2,500, we're not going to trust P. So the first table I made, the sample size was more than 33,000. P was not trustworthy. We'll throw that one out. This one, the sample size is less than 2,500. It fits my rule. We can trust P. So I'm going to say, yes, P probably really is 77.77. It exceeds 0.05. 77% chance that our results are due to randomness. Therefore, that table is not statistically significant because P is greater than 0.05. Now you might be asking, well, how do we assess statistical significance when we cannot trust P? Well, if you take statistics, there are a number of other tests, and you can see some of them down here underneath the table. In this class, we're not going to use them. We're going to use another test that I call delta. Delta is the Greek letter equivalent to D. Mathematicians use it to stand for difference. Difference means subtraction. So it's very simple. We're just going to subtract the lowest percentage in the row from the highest percentage in the row. So in this example, 39.3 minus 38.5 is what? 0.8%. Delta is 0.8%. You see what I did there? I subtracted 38.5 from 39.3. The result is 0.8. The difference between these two numbers, the highest and the lowest, is 0.8%. That's all delta is. It's the difference between the highest number, the highest percentage in a row, and the lowest percentage in the row. So write that in your notes. How do you calculate delta? Subtract the highest percentage in a row from the lowest percentage in a row. And we're looking for the absolute value. It doesn't matter if it's negative or positive. We're just looking at the difference between the two. Delta D for difference. Now, my personal rule of thumb is that if delta is 10% or more, then I'm going to accept that table as being statistically significant. 10%, a 10% difference between the categories of my independent variable, I think, are pretty meaningful. Now, that's, again, just my personal rule. We'll use that for this course, a delta of at least 10%. Now, there might be some cases where, well, let's save this for the next video.